Imagine four massive galaxy clusters slamming into each other right now, 7 billion light-years away, unleashing chaos so wild it warps light itself and shreds the fabric of space. This brutal cosmic smash-up in MACS J0717 isn't just a crash, it's a battlefield where invisible forces battle plasma hotter than the sun's core, revealing secrets no Earth lab could dream of recreating. If you're hooked on this mind-bending violence, smash that like button, subscribe for more deep space thrills, and stick around because the mayhem barely begins. Prepare yourselves, we begin. The story of MACS J0717 began not with a dramatic announcement, but with a quiet anomaly that refused to make sense. A faint shimmer in the constellation Aries that caught the attention of astronomers scanning the deep cosmos for gravitational lenses in the early 2000s. They were using the Hubble Space Telescope, that iconic eye in orbit that has revealed so many wonders, and what they found wasn't just one gravitational lens bending light around a massive object, but something far stranger and more violent, a region where light from distant galaxies behind this cosmic structure was being stretched and distorted in multiple directions at once, creating arcs and streaks that suggested not a single cluster, but a chaotic pileup of enormous proportions. At first, researchers thought they were looking at a typical galaxy cluster, those vast collections of hundreds or thousands of galaxies bound together by gravity. But as they gathered more data from different wavelengths, particularly X-ray observations from the Chandra X-ray Observatory, the true nature of this beast started to emerge, and it was unlike anything they had anticipated. The X-ray images revealed massive clouds of superheated plasma, glowing with the energy of collisions, and these clouds weren't arranged in the neat, roughly spherical shape you'd expect from a relaxed cluster that had settled into equilibrium over billions of years. Instead, they were elongated, twisted, and fragmented, with bright knots and trailing tails that screamed violence and upheaval. Teams of astrophysicists began piecing together velocity data from individual galaxies within this structure, measuring how fast they were moving relative to each other using spectroscopy. And what they discovered was staggering. There were four distinct groups of galaxies, all converging on the same point in space, each group containing hundreds of galaxies and traveling at speeds exceeding 2,000 kilometers per second, which is fast enough to cross the entire United States in less than 2 seconds. These weren't gentle drifts or slow mergers playing out over cosmic timescales. This was a high-speed demolition derby happening on the grandest scale imaginable, and the fact that all four groups were colliding almost simultaneously made MACS J0717 one of the most complex and energetic merger events ever witnessed. The distance to this collision zone was calculated to be around 5.4 billion light-years away, meaning the light we see today left that region when our own solar system was still in its infancy. Yet even across that vast gulf of space and time, the violence is unmistakable. Hubble's sharp optical and near-infrared vision allowed astronomers to count the galaxies involved, and the numbers were mind-boggling. Over 300 massive galaxies crammed into a region about 13 million light-years across, which might sound huge, but for that many galaxies, it's incredibly compact and dense, like packing dozens of cities into an area the size of a single neighborhood. Each of those galaxies contains hundreds of billions of stars, and as the groups plow into each other, the gravitational forces are immense, pulling and stretching everything in their path. But here's where it gets even more fascinating. When astronomers compared the distribution of visible matter, the stars and glowing gas, with the distribution of total mass inferred from gravitational lensing, they found a massive discrepancy. The lensing revealed that most of the mass wasn't in the galaxies or the hot plasma at all, but in something invisible that was spreading out in a different pattern entirely. This was the first major clue that dark matter, that mysterious substance that doesn't emit or absorb light, but makes up the majority of matter in the universe, was behaving differently from the ordinary matter during the collision. A revelation that would become central to understanding what makes MACS J0717 so scientifically valuable. Additional observations came from radio telescopes, which detected enormous structures called radio relics and radio halos. These are regions where electrons are accelerated to nearly the speed of light by shockwaves and magnetic fields, emitting radio waves that trace out the battle scars of the collision. The radio relics appear as giant arcs, stretching millions of light years across the cluster's edges, marking where shock fronts from the colliding groups have swept through the intergalactic medium like cosmic tsunamis, and the radio halos glow from the central regions where turbulence and magnetic field amplification are at their peak. Putting all these observations together, from optical to X-ray to radio, astronomers realized they were witnessing one of the most violent and complex events in the modern universe, a quadruple merger that was still actively unfolding, with shock waves propagating outward, plasma sloshing around, dark matter, halos interpenetrating, and galaxies being flung about like leaves in a hurricane. The discovery wasn't just about finding another galaxy cluster. It was about finding a natural laboratory where the fundamental physics of the universe, gravity, dark matter, plasma dynamics, and structure formation, were all being tested under the most extreme conditions imaginable, conditions that no computer simulation could fully capture and no experiment on Earth could ever hope to replicate. Early papers, published on MACS J0717, described it as a train wreck and a cosmic construction site, and those metaphors barely do justice to the sheer scale and energy involved, because what we're really talking about is the collision of structures, each containing the mass of 1,000 trillion suns, all crashing together at speeds that defy everyday intuition. And the fact that this was discovered at all speaks to the power of multi-wavelength astronomy, the ability to observe the same region of space in many different ways, and piece together a complete picture from those fragments. Because if astronomers had relied on optical light alone, they would have seen the galaxies, but missed the plasma. And if they'd used only X-rays, they would have seen the hot gas, but missed the dark matter. And if they'd stuck to radio observations, they would have seen the shock structures, but missed the detailed motions of individual galaxies. It was the combination of all these perspectives that revealed MACS J0717 as the chaotic, multi-stage cosmic pileup it truly is, and it set the stage for decades of follow-up observations and theoretical work aimed at understanding how such extreme events shape the evolution of the universe. What started as a faint shimmer and a puzzling gravitational lens had been unraveled into one of the most spectacular and scientifically rich discoveries in modern cosmology. A place where the universe's violent side is on full display, and where every new observation raises more questions about the hidden forces and unseen matter that dominate the cosmos. To truly grasp the scale of mayhem unfolding in MACS J0717, you have to abandon every earthly comparison and venture into numbers so vast they start to lose meaning. Yet somehow, they're all real and measurable, and happening right now across a patch of universe so distant. Its light has been traveling toward us since before Earth had continents in their current form. The collision zone spans roughly 13 million light-years from end to end, which means if you could freeze time and measure the distance from one edge of this cosmic battlefield to the other, light itself, moving at 300,000 kilometers per second, would take 13 million years to make that journey. And to put that in perspective, that's wider than the distance from our Milky Way to the Andromeda Galaxy, and back more than 6 times over. Within this colossal volume, 4 separate galaxy groups are converging, each one a massive structure in its own right, containing hundreds of individual galaxies. And when you add up all the galaxies involved in this pileup, you're looking at more than 300 massive systems, each hosting hundreds of billions of stars, which means the total stellar population caught up in this collision is somewhere in the ballpark of tens of quadrillions of stars, a number so absurdly large that if you tried to count them one per second, you'd need trillions of years to finish. But stars, as numerous as they are, represent only a tiny fraction of the mass involved here, because the real heavyweight in this cosmic demolition derby is the dark matter, that invisible substance that doesn't glow or emit any radiation, but makes its presence known through gravity alone. And in MACS J0717, the dark matter component contributes the equivalent mass of roughly 10 to the power of 15 solar masses, or about 1,000,000 billion times the mass of our Sun, which is a figure that challenges the imagination, but becomes even more staggering when you realize that most of this mass is completely invisible and can only be detected by how it warps the fabric of space-time around it. The visible matter, primarily in the form of hot X-ray emitting plasma, accounts for another roughly 10% of the total mass, and even that plasma is extraordinary in its own right because it's been heated to temperatures exceeding 100 million degrees Kelvin, which is several times hotter than the core of the Sun where nuclear fusion occurs. And at these temperatures, the gas is fully ionized, meaning electrons have been stripped from their atoms, and the plasma glows intensely in X-rays as particles collide and release energy. The amount of energy being released in this collision is almost incomprehensible. Estimates suggest that the kinetic energy alone, just from the motion of all these galaxies and gas clouds plowing into each other at thousands of kilometers per second, is equivalent to billions upon billions of supernovae going off simultaneously. And that doesn't even account for the gravitational potential energy being converted into heat and radiation as matter falls deeper into the combined gravitational well of the merging clusters. The four groups colliding here are moving at relative velocities that have been measured at around 2,000 to 3,000 kilometers per second, which is roughly 1% the speed of light. And while that might not sound like much compared to light itself, it's absolutely blistering by cosmic standards, faster than anything in our solar system moves, and fast enough that the kinetic energy of a single galaxy in this collision dwarfs the total energy output of all the stars in that galaxy, combined over millions of years. When structures moving at these speeds collide, the results are cataclysmic. The intergalactic plasma, which is diffuse but still dense enough to interact through electromagnetic forces, slams together and creates shockwaves that propagate outward at supersonic speeds, heating the gas to those extreme temperatures and accelerating particles to near-light speeds, while the galaxies themselves, being mostly empty space between their stars, pass through each other largely unscathed on the stellar level, though their dark matter halos and the gravitational tides they create wreak havoc on their shapes and trajectories. The shock fronts generated by these collisions have been measured to extend over millions of light years, creating vast radio-emitting structures called relics that mark the boundaries of the collision zone, like cosmic scars. And these relics shine in radio wavelengths because the shock waves compress and amplify magnetic fields, which in turn accelerate electrons to relativistic speeds, causing them to spiral around the field lines and emit synchrotron radiation that radio telescopes can detect from billions of light years away. Inside the central region, where all four groups are converging, the environment is even more chaotic. Turbulence stirs the plasma like a giant cosmic blender, creating eddies and currents that stretch for hundreds of thousands of light years. And this turbulence also amplifies magnetic fields through a process called dynamo action, where the motion of the electrically conducting plasma generates and sustains magnetic energy that adds yet another layer of complexity to the physics at play. The total mass of MACS J0717, combining dark matter, hot gas, and galaxies, is estimated to be around 3 quadrillion solar masses, making it one of the most massive structures known in the observable universe. And this mass is so large that it creates a gravitational well deep enough to bend light from galaxies far behind it by significant angles, producing multiple images and arcs that astronomers use to map out where the mass is distributed. And those maps reveal that the dark matter isn't smoothly distributed, but is clumped into several distinct halos corresponding to the 4 infalling groups, each halo trailing behind its associated galaxies and gas, because dark matter interacts only through gravity and doesn't experience the drag forces that slow down the visible matter. The scale of this separation between dark matter and gas provides crucial evidence for dark matter's existence and properties, because if dark matter were just an illusion or an error in our understanding of gravity, you wouldn't expect to see this kind of spatial offset. But here it is, plain as day in the lensing maps and X-ray images, showing that something massive and invisible is present and behaving exactly as predicted by the cold, dark matter model. The energy budget of this collision is staggering in another way too, because as the gas heats up and radiates X-rays, it's losing energy to space. And naively you might think this would cool the cluster down over time, but the gravitational energy being released as the structures merge keeps pumping heat back into the system, creating a balance that sustains the extreme temperatures over millions of years. And yet, even with all this energy input, some of the gas does manage to cool, and presumably forms new stars in the galaxies, caught up in the merger, though the rate of star formation in such a violent environment is still a matter of active research. To make the scale even more tangible, consider that the shockwaves racing through MACS J0717 are moving at speeds around 1,000 kilometers per second, and they're carrying enough energy to heat gas across volumes larger than entire galaxy superclusters. And if you could somehow stand at the edge of one of these shock fronts, you'd witness a wall of superheated plasma, taller and wider than thousands of galaxies, advancing at a rate that would cross the distance from Earth to the Sun in less than 2 hours. Although, of course, standing anywhere near this collision would be instantly fatal in ways that defy description, given the temperatures, radiation levels, and gravitational forces involved. The timescales involved are equally mind-bending. The entire merger event, from the first tentative interactions between the groups to the final coalescence into a single massive cluster, will likely take several billion years to complete, meaning that what we're seeing right now is just a snapshot of a process that began before our sun was born and will continue long after our sun has died. And yet, within that slow cosmic ballet, there are moments of extreme violence happening on much shorter timescales. Shock waves crossing the cluster in just a few million years, galaxies making close passes and being flung onto new orbits in tens of millions of years, and plasma eddies swirling and dissipating over hundreds of millions of years. The spatial scale also means that light itself takes millions of years to cross from one side of the collision to the other. So different parts of MACS J0717 that we observe simultaneously in our telescopes are actually seeing each other at different times, separated by the light travel time between them, which adds a strange relativistic twist to the whole scenario, where cause and effect across the cluster are smeared out over epochs longer than the entire history of multicellular life on Earth. And looming over all of this is the invisible hand of dark matter, making up roughly 85% of the total mass and dictating the gravitational dynamics that drive the entire collision, yet remaining completely undetectable, except through its gravitational influence, a ghostly presence that outweighs everything we can see by a factor of 6 to 1, and shapes the fate of this cosmic train wreck in ways we're only beginning to understand, because every simulation of cluster mergers depends critically on assumptions about dark matter's properties, and MACS J0717 provides one of the best natural experiments to test whether those assumptions hold up under the most extreme conditions the universe can offer. When four galaxy groups collide at thousands of kilometers per second, the intergalactic medium doesn't just quietly step aside. It erupts in a display of physics so violent and energetic that it creates some of the most extreme environments in the known universe. And in MACS J0717, this fury manifests primarily through shockwaves, those invisible cosmic tsunamis that race through the thin plasma between galaxies and leave trails of destruction and transformation in their wake. To understand what's happening here, you need to picture the intergalactic medium not as empty space, but as a tenuous gas, incredibly thin by Earth standards, with densities far lower than the best vacuum we can create in laboratories, yet spread across such vast volumes that the total mass adds up to more than all the stars in all the galaxies combined. And this gas, mostly hydrogen and helium, left over from the Big Bang, has been sitting in the gravitational wells of these galaxy groups for billions of years, slowly accumulating and heating up to temperatures of tens of millions of degrees, just from the gentle compression of gravity. But when the groups collide, gentle goes out the window, because now you have massive clouds of this already hot plasma, each cloud stretching millions of light years across and containing the mass of trillions of suns, slamming into each other at speeds around 2,000 kilometers per second. And at these velocities, the collision is supersonic, meaning the plasma is moving faster than sound waves can travel through it. And whenever something moves through a medium faster than the medium's sound speed, you get a shock wave, a sharp discontinuity, where pressure, density, and temperature all jump dramatically as the material piles up and compresses. In MACS J0717, there are multiple shock waves propagating through the cluster from different directions, each one generated by the collision of a different pair of infalling groups. And these shocks are not small or weak. They're enormous structures spanning millions of light years with energy densities that dwarf anything we can produce on Earth. And as they plow through the intergalactic medium, they heat the gas to temperatures exceeding 100 million degrees Kelvin, which is hot enough that the thermal energy of individual particles approaches the energies we see in particle accelerators. And at these temperatures, the plasma radiates intensely in X-rays, which is how astronomers first detected these shock fronts using the Chandra X-ray Observatory. The X-ray images of MACS J0717 reveal a complex morphology that looks nothing like the smooth, relaxed clusters that have settled into equilibrium. Instead, you see elongated plumes, bright knots, trailing tails, and sharp edges that mark the locations of shock fronts. And by carefully analyzing the temperature and brightness variations across these features, astrophysicists can map out where the shocks are, how fast they're moving, and how much energy they're depositing into the gas. One of the most dramatic features is a giant shock front on the outskirts of the cluster, detected both in X-rays and through radio observations, where the collision has driven a bow shock into the surrounding intergalactic medium. Much like a supersonic jet creates a shock wave in Earth's atmosphere. And this particular shock has been measured to have a Mach number around 3, meaning it's traveling at 3 times the local sound speed, which in this plasma corresponds to velocities around 1,500 kilometers per second. And as the shock passes through a given region of gas, it compresses it by a factor of about 4 and heats it from perhaps 10 million degrees to over 40 million degrees, almost instantaneously on cosmic timescales, within just a few thousand years as the shock front sweeps past. But the heating isn't uniform or smooth, because the shock itself is unstable and turbulent, with ripples and corrugations across its surface that amplify as the shock propagates. And behind the shock, the gas doesn't just settle down into a new equilibrium, but continues to churn and swirl with turbulent eddies that can persist for hundreds of millions of years. And this turbulence is crucial because it amplifies magnetic fields through dynamo processes, taking weak seed fields and stretching and twisting them until they reach strengths of several microgauss, which might sound tiny compared to Earth's magnetic field, but across the vast volumes of a galaxy cluster these fields, contain enormous amounts of energy and play a major role in confining and accelerating high-energy particles. Speaking of particle acceleration, the shockwaves in MACS J0717 are incredibly efficient at taking thermal particles, those that are just bouncing around randomly with energies corresponding to the gas temperature, and boosting a small fraction of them to relativistic speeds, creating cosmic rays that carry energies millions or even billions of times higher than the average particle. And this process, called diffusive shock acceleration, happens because particles can bounce back and forth across the shock front multiple times, gaining a little energy with each crossing, and the few lucky particles that get trapped in this acceleration cycle long enough can reach energies approaching those of the highest energy cosmic rays ever detected, although most don't make it that far, and instead radiate away their energy as synchrotron radiation when they spiral around magnetic field lines. This synchrotron radiation is what makes the shock waves visible to radio telescopes, because the accelerated electrons emit radio waves as they gyrate around the amplified magnetic fields, and the radio observations of MACS J0717 reveal spectacular structures called radio relics. These are enormous arcs and filaments stretching across the cluster's periphery, each one marking the location of a major shock front. And some of these relics extend over 5 million light-years, making them among the largest coherent structures associated with any galaxy cluster. The radio emission traces out the geometry of the collision in exquisite detail, showing not just where the shocks are, but also how they've evolved over time, because different parts of a relic can have different spectral properties, depending on how long ago the shock passed through, and how much time the accelerated electrons have had to lose energy through radiation. And by mapping these variations, astronomers can reconstruct the history of the collision, figuring out which group hit which and when, almost like cosmic forensics, where the evidence is written in radio waves and X-rays across millions of light-years. The central regions of MACS J0717 tell a different but equally violent story, because here multiple shocks have collided and interfered with each other, creating a tangled mess of compressed gas, turbulent flows, and amplified magnetic fields that astronomers describe as a radio halo. Unlike the relics, which are relatively sharp and well-defined, the halo is a diffuse glow of radio emission coming from the cluster core, where turbulence, rather than shocks, is the dominant mechanism for particle acceleration. And this turbulence, stirred up by the ongoing merger and sustained by the gravitational energy being released as matter falls into the cluster's center, keeps re-accelerating particles and preventing the radio emission from fading away. The distinction between relics and halos is important because it tells us about different physical processes at work. Relics are signposts of shock acceleration happening at the collision boundaries, where fresh material is being processed for the first time, while halos indicate ongoing turbulent re-acceleration in regions that have already been shocked and are now settling into a new, but still violently turbulent equilibrium. And MACS J0717 has both, making it a natural laboratory for studying the full range of non-thermal processes that occur in cluster mergers. The energy budget of these shocks is staggering. Estimates suggest that anywhere from 10 to 30% of the kinetic energy from the collision gets converted into thermal energy and turbulence in the gas, while a smaller, but still significant fraction, perhaps a few percent, goes into accelerating particles to relativistic energies and amplifying magnetic fields. And even a few percent of the total collision energy is an enormous absolute amount, given that we're talking about the kinetic energy of structures containing quadrillions of solar masses, moving at thousands of kilometers per second. So the shocks in MACS J0717 are injecting energy into the intergalactic medium at rates comparable to billions of supernovae per year, sustained over millions of years, which is an energy output that staggers the imagination. The temperatures behind the shocks, over 100 million degrees in some regions, create an environment where the physics gets truly exotic. At these temperatures, collisions between particles are violent enough that they emit hard X-rays and even gamma rays, and the plasma is so hot that it has enormous pressure, exerting forces that can push galaxies around or distribute gas on scales of millions of light years. Yet despite these extreme conditions, the shocks are also incredibly efficient radiators, emitting so much X-ray radiation that they glow like beacons across half the observable universe, which is both a blessing and a curse for astronomers, because the intense emission makes them easy to detect, but also means the gas is losing energy rapidly and cooling in some regions, leading to complex multiphase structures where hot shocked gas, warm cooling gas, and cold dense clumps all coexist in the same volume. One of the most surprising discoveries from studying the shocks in MACS J0717 came from comparing the locations of the X-ray emission, which traces the hot gas, with the gravitational lensing maps, which trace the total mass, including dark matter, because in several regions, the two don't line up at all. The X-ray emission shows sharp edges and compressed features where shocks have passed through, while the lensing maps show smooth, extended dark matter distributions that seem to have passed right through the collision without being affected. And this spatial offset is powerful evidence that dark matter doesn't interact through electromagnetic forces, or even through collisions, the way normal matter does. Instead, it only feels gravity. So while the gas slams together and shocks and heats up, the dark matter halos just glide through each other like ghosts, their particles passing by without ever touching. And this collisionless nature is exactly what theories predict. But seeing it demonstrated so clearly in nature is one of the great triumphs of modern observational cosmology. The shock waves also create secondary effects that ripple through the cluster ecosystem. For instance, they can trigger or suppress star formation in galaxies that happen to be in their path. A galaxy moving through a shock front experiences a sudden ram pressure as the shock-compressed gas pushes against the galaxy's own interstellar medium, and this pressure can either compress gas clouds within the galaxy to the point where they collapse and form stars, a process called shock-induced star formation, or it can strip gas out of the galaxy entirely, removing the raw material for future star formation, and effectively killing the galaxy, turning it into a red and dead elliptical over the following billion years. Observations of galaxies in MACS J0717 show evidence for both processes happening. Some galaxies caught in the collision zone show enhanced star formation rates, with bright blue colors indicating young massive stars, while others have been stripped of their gas and show the red colors of old stellar populations, with no new stars being born. And the balance between these outcomes depends on the details of each galaxy's trajectory, how fast it's moving, what angle it hits the shock at, and how much gas it had to begin with. The magnetic fields amplified by the shocks also have far-reaching consequences, because once you have strong magnetic fields permeating the cluster, they affect how the plasma behaves, suppressing thermal conduction across field lines and creating anisotropies in pressure and temperature that wouldn't exist in a purely hydrodynamic system. And these magnetic effects can alter the long-term evolution of the cluster, influencing how gas cools and flows, and where the next generation of shocks will form as the merger continues. Radio polarization observations of MACS J0717 reveal that the magnetic fields are indeed highly ordered in some regions, particularly near the shock fronts, where the compression and shearing of the plasma have aligned the field lines, while in other regions the fields are tangled and chaotic, reflecting the turbulent conditions in the cluster core. And mapping out these magnetic structures is an ongoing effort that requires sensitive radio observations at multiple frequencies and polarizations. The shockwaves in MACS J0717 are not static features, but dynamic, evolving structures. They propagate outward at speeds of hundreds to thousands of kilometers per second, eventually reaching the edges of the cluster and beyond, where they'll merge with the even more diffuse intergalactic medium, and perhaps trigger new rounds of structure formation by compressing gas in filaments connecting to other clusters. And as they propagate, they gradually weaken, their Mach numbers decreasing as they spread out over larger areas and dissipate their energy into heat and turbulence. But even weakened, they're still formidable, capable of heating gas and accelerating particles across scales that dwarf individual galaxies. Behind them, they leave a transformed medium. Gas that was cool and quiescent is now hot and turbulent, seeded with relativistic particles and threaded with amplified magnetic fields. And this transformed medium will shape the future evolution of the cluster, affecting everything from galaxy formation to the eventual fate of the structure as it continues to merge and grow over the next several billion years. And in this sense, the shockwaves are not just destructive forces, but creative ones. They're agents of change that inject energy, redistribute matter, and set the stage for the next chapter in the cluster's history. The most haunting aspect of the cosmic collision zone isn't what you can see through telescopes, but what remains forever invisible. The dark matter that makes up roughly 85% of all the mass involved in this catastrophic merger, yet refuses to emit, absorb, or reflect a single photon of light at any wavelength. And it's this ghostly component that truly dominates the physics of MACS J0717, shaping the trajectories of galaxies, bending light from the distant universe, and proving, through its behavior during the collision, that it operates by rules fundamentally different from the ordinary matter we're made of. When astronomers first began mapping the mass distribution of this cluster using gravitational lensing, they expected to find that the bulk of the mass would align with the bright X-ray emission from the hot plasma, because in a relaxed, stable cluster, that's usually the case, the dark matter, gas, and galaxies all settle into roughly the same gravitational wells, and their distributions overlap. But MACS J0717 is anything but relaxed, and what the lensing maps revealed was startling. The peaks of mass inferred from how strongly different regions bent background light didn't line up with the peaks of X-ray emission at all. In several areas, they were offset by hundreds of thousands of light years. And this separation told a profound story about how different forms of matter behave when subjected to the violence of a high-speed collision. The gravitational lensing technique that revealed this separation works by measuring how light from distant galaxies, those lying billions of light years behind MACS J0717, gets distorted as it passes through the cluster's gravitational field, because according to Einstein's general relativity, mass warps the fabric of spacetime itself, and light traveling through that warped spacetime follows curved paths. So from our perspective on Earth, the images of those background galaxies appear stretched into arcs, magnified, and sometimes multiply-imaged if the light takes several different paths around the cluster. And by carefully analyzing the shapes and positions of hundreds of these lensed galaxies, astronomers can reconstruct a map of the total mass distribution, regardless of whether that mass is visible or invisible, luminous or dark. For MACS J0717, teams using the Hubble Space Telescope identified over 50 separate multiply-image systems, meaning more than 50 background galaxies, whose light had been bent so severely by the cluster's gravity that each galaxy appeared in 2, 3, or even more locations on the sky. And by measuring the precise positions of these multiple images and feeding that information into sophisticated lens modeling software, researchers built detailed maps showing where the mass was concentrated and those maps revealed 4 distinct peaks corresponding to the 4 infalling galaxy groups, each peak containing roughly a few times 10 to the 14th solar masses of material. And when you add up all 4 peaks, plus the more diffuse mass in between, you get a total mass approaching 2 times 10 to the 15th solar masses within the central megaparsec, making this one of the most massive structures ever mapped in such detail. But here's where it gets truly revealing. When the researchers overlaid their lensing-derived mass maps onto the X-ray images from Chandra, which show where the hot intergalactic plasma is located, they found clear offsets. The X-ray emission was brightest in regions trailing behind the mass peaks, as if the gas had been left behind while something else, the dark matter, had pushed ahead. And this makes perfect sense once you understand the fundamental difference between how dark matter and ordinary matter interact. The gas clouds from the 4 infalling groups are made of charged particles, protons and electrons mostly. And when 2 clouds of charged particles try to pass through each other at thousands of kilometers per second, they collide. They interact through electromagnetic forces. They experience drag and friction, and they slow down, transferring their kinetic energy into heat and producing the brilliant X-ray emission we observe. But dark matter doesn't experience any of these forces. It doesn't carry electric charge, so it doesn't interact electromagnetically, and crucially, it appears to be collisionless, meaning dark matter particles from one halo can pass right through dark matter particles from another halo without bouncing off or slowing down. They just glide past each other like ghosts, because the only force dark matter responds to is gravity, and gravity at the particle level is far too weak to cause individual dark matter particles to scatter off one another during a collision. This collisionless nature of dark matter has profound implications, because it means that when the 4 groups in MACS J0717 came together, their dark matter halos interpenetrated cleanly. The dark matter from each group continued on roughly ballistic trajectories, determined only by the large-scale gravitational potential of the combined system, while the gas crashed and shocked and heated and radiated and got left behind, and the galaxies, being mostly empty space between their stars, also passed through the collision relatively unscathed. So what you end up with is a spatial separation between 3 components: the dark matter out in front moving fastest, the galaxies moving with the dark matter because they're small and collisionless at the stellar level, and the gas trailing behind glowing bright in X-rays as it dissipates the violence of the collision. And this 3-way separation is exactly what's observed in MACS J0717, and it provides some of the most direct evidence we have that dark matter really exists as a distinct physical substance rather than being an artifact of misunderstood gravity. The dark matter maps, derived from lensing, also reveal substructure within each of the 4 main peaks, suggesting that even these individual infalling groups aren't monolithic, but are themselves made up of smaller clumps and filaments that are in the process of merging. And this hierarchical picture of structure formation, where small structures merge to form larger ones, which merge to form even larger ones, is a fundamental prediction of the cold dark matter model of cosmology. And MACS J0717 is essentially a live snapshot of this process in action, catching dark matter in the act of assembling one of the universe's largest structures. Measuring the properties of dark matter during these collisions also allows scientists to constrain how dark matter interacts with itself, because if dark matter particles could scatter off each other even rarely, you'd expect to see some smearing or smoothing of the dark matter distribution. In regions where 2 halos overlap, the collisions would transfer momentum between particles and cause the peaks to spread out. But the lensing maps of MACS J0717 show sharp, well-defined peaks with no obvious signs of such scattering, which means that if dark matter does self-interact the cross-section, the effective size of each particle as a target for collisions, must be incredibly tiny, much smaller than the cross-sections for ordinary particle interactions. And by comparing the observed dark matter distributions to computer simulations of colliding clusters with different assumed self-interaction cross-sections, researchers have been able to place upper limits on this quantity, finding that dark matter self-interactions must occur less than about once per particle per 10 billion years on average, making dark matter even more ghostly than previously thought. The total dark matter mass in MACS J0717 is staggering, something like 1.7 times 10 to the 15th solar masses, when you integrate over the entire cluster out to a radius of several megaparsecs. And to put that in perspective, if you took every star in the Milky Way, all 400 billion of them, and multiplied by several million, you'd approach the dark matter mass in this single cluster, and yet not one particle of that enormous mass has ever been directly detected in a laboratory. We know it's there only through its gravitational effects, the way it bends light, the way it holds galaxies in the cluster together against their random motions, and the way its distribution separates from the gas during collisions, which is perhaps the most convincing evidence of all, because it's hard to explain that separation with any modified gravity theory. You really need a collisionless mass component to reproduce what we see. The dark matter also extends far beyond the visible extent of the cluster. Lensing measurements show significant mass concentrations at projected distances of several megaparsecs from the cluster core, and these outer structures are connected to the main cluster by filaments, long tendrils of dark matter threaded with galaxies and gas that follow the cosmic web. The large-scale network of matter that defines the universe's structure on the biggest scales, and one particularly prominent filament has been mapped extending southeast from MACS J0717, funneling additional galaxies and dark matter toward the collision zone. And this filament is important because it shows that cluster mergers aren't isolated events happening in empty space, but are fed by the cosmic web. Matter streams along these filaments from the surrounding universe and dumps into regions like MACS J0717, where it adds to the chaos and contributes to building what will eventually become a massive supercluster. Studying the dynamics of the dark matter in MACS J0717 also requires understanding the velocities, not just where the dark matter is, but how fast it's moving. And this is trickier because dark matter doesn't emit light, so you can't measure Doppler shifts directly. Instead, astronomers use the galaxies as tracers, measuring the redshifts of hundreds of cluster member galaxies to build up a picture of the velocity field. And since galaxies are embedded in dark matter, halos and generally move with the dark matter, their velocities give you information about the dark matter's motion. And what those measurements show is that the four groups are moving relative to each other at speeds around 2,000 to 3,000 kilometers per second, which translates to dark matter particles in one halo passing through dark matter particles in another halo at incredible velocities. And if there were any significant interaction between those particles, you'd expect to see evidence in the form of shocked dark matter or displaced peaks. But you don't. The dark matter just sails through as if the other halo weren't even there. The separation between dark matter and gas in MACS J0717 also has implications for understanding the thermodynamics of the cluster, because the gas that's been left behind by the dark matter is where all the shock heating occurs. The gas is what lights up in X-rays, and the amount of X-ray emission depends on the gas density squared. So regions where the gas has been compressed by shocks or by falling into the dark matter potential wells shine very brightly, and by comparing the temperature and density profiles of the gas to the dark matter distribution, researchers can figure out how much energy has been injected into the gas by the collision and how that energy is being dissipated through radiation and turbulence. And those energy budgets in turn tell you about the efficiency of different physical processes and help calibrate models of cluster formation that are used to interpret observations of clusters at all redshifts throughout cosmic history. One of the most sophisticated aspects of the dark matter analysis involves creating three-dimensional mass models, because what you see in a lensing map is a projection. All the mass along the line of sight gets lumped together, but by combining lensing data at different wavelengths, by using the distribution of galaxies with measured redshifts to trace structure in the third dimension, and by comparing to the X-ray emission, which has its own depth information encoded in spectral features, researchers can start to untangle the three-dimensional structure and understand not just where the mass is on the sky, but how it's arranged in depth, which peaks are in the foreground, which are in the background, and how they're moving relative to each other. And for MACS J0717, such analyses have revealed that the four main groups are not all at the same distance. They're spread out over several megaparsecs in the line of sight direction, and they're converging from different angles, creating the complex, tangled geometry we observe. The dark matter in MACS J0717 also serves a secondary role as a natural telescope because its gravity is so strong that it acts as a gravitational lens, magnifying and brightening galaxies that lie far behind the cluster, and some of these background galaxies are so distant that their light was emitted less than 1 billion years after the Big Bang, making them some of the earliest galaxies ever formed. And without the magnification provided by the dark matter in MACS J0717, these infant galaxies would be far too faint to study, even with the most powerful telescopes we have. But the cluster's gravity boosts their apparent brightness by factors of 10 or more in some cases, turning MACS J0717 into a cosmic magnifying glass that lets us peer into the universe's first billion years. And this is one of the reasons this cluster is part of the Hubble Frontier Fields program, a major observational campaign that has devoted enormous amounts of telescope time to imaging 6 of the most powerful gravitational lenses in the sky. And the science returned from those observations has been spectacular, revealing not just the properties of the cluster itself, but also a treasure trove of high redshift galaxies that are teaching us about the epoch of reionization, the formation of the first stars, and the early assembly of galactic structure. The dark matter component of MACS J0717 ultimately determines the cluster's fate, because while the gas can radiate away energy and eventually cool and settle, and while the galaxies can experience dynamical friction and spiral toward the cluster center, the dark matter, having no way to dissipate energy except through gravitational interactions, will retain most of its kinetic energy for billions of years, continuing to slosh around in the gravitational potential well of the merged system. And over time, as the 4 groups complete their merger and the system virializes, meaning it reaches a state where the kinetic and potential energies are in equilibrium, the dark matter will settle into a roughly spherical halo surrounding the new supercluster, and that halo will be enormous, extending for tens of megaparsecs and containing the equivalent mass of 10,000 Milky Way galaxies, all of it invisible, all of it detectable only through its gravitational influence, a cosmic ghost made of particles we've never seen, that nonetheless governs the largest structures in the universe.
解剖紧握
The cosmic collision zone at MACS J0717 doesn't just showcase destruction on an unimaginable scale. It also performs one of nature's most spectacular magic tricks, transforming violence into discovery by bending the very fabric of space-time so profoundly that it acts as a natural telescope magnifying galaxies from the earliest epochs of cosmic history. And this gravitational lensing effect, a direct consequence of Einstein's general relativity, turns out to be one of the most powerful tools astronomers have for studying both the cluster itself and the ancient universe that lies far beyond it. The basic physics of gravitational lensing is beautiful in its elegance. According to Einstein's theory, mass doesn't just pull on other mass through some mysterious force acting at a distance. Instead, Mass warps the geometry of space-time itself, creating curves and valleys in the four-dimensional fabric of the universe. And when light travels through this warped space-time, it follows the curves, taking paths that appear bent from our perspective. So when you have an incredibly massive object, like MACS J0717, with its quadrillion solar masses concentrated in a relatively small region, the space-time curvature becomes severe enough that light from galaxies, billions of light years behind the cluster, gets deflected by measurable angles as it passes by, and depending on the exact geometry, the alignment between the background galaxy, the cluster, and us, that light can be magnified, distorted into arcs, or even split into multiple images of the same object, appearing in different parts of the sky. For MACS J0717, this lensing power is extraordinary. The cluster's mass is so great, and its distribution so concentrated, that it creates what astronomers call a strong gravitational lens, one of the most powerful natural telescopes in the observable universe. And when you point Hubble or other high-resolution telescopes at this region, you don't just see the 300 or so galaxies that are members of the cluster itself. You also see hundreds of background galaxies whose images have been warped into long, graceful arcs, stretching across the field of view. Some of these arcs curve for tens of arc seconds across the sky, which might not sound like much, but at the distances involved corresponds to light being deflected across hundreds of thousands of light years. And the shapes of these arcs encode information about the mass distribution of the cluster, allowing astronomers to map out where the dark matter is, even though they can't see it directly. The magnification provided by gravitational lensing is particularly valuable because it allows us to study galaxies that would otherwise be completely inaccessible. Some of the background galaxies, lensed by MACS J0717, are so distant that their light was emitted less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first generations of galaxies were just beginning to form. And at those distances, and that early in cosmic time, galaxies are intrinsically faint. They haven't had time to build up large populations of stars, and they're receding from us so fast, due to the expansion of the universe, that their light gets redshifted out of the optical wavelengths and into the infrared, where detection becomes more challenging. But the gravitational lens provided by MACS J0717 can boost the apparent brightness of these ancient galaxies by factors of 10, 20, or even 50. In some cases, effectively turning a galaxy that would be barely detectable, even with the longest exposures, into one that can be studied in detail. Its spectrum measured, its star formation rate determined, its chemical composition analyzed. This magnification isn't uniform across the field. It depends on exactly where a background galaxy happens to lie, relative to the cluster's mass distribution. Galaxies that pass very close to the critical curves, the regions where the lensing effect is strongest, can be magnified enormously and stretched into long, thin arcs, while those farther from the critical curves experience weaker lensing and appear as less distorted ellipses. And by mapping out how the magnification varies across the field, astronomers can reconstruct the lens model, essentially reverse engineering the mass distribution that must be present to produce the observed pattern of distortions. And for MACS J0717, this has been done with extraordinary precision using over 50 multiply-imaged galaxies. These are background sources that appear in 2, 3, or even more locations, because light from them has taken multiple different paths around the cluster, each path experiencing different amounts of deflection and time delay. The multiply image systems are particularly valuable because they provide strong constraints on the lens model. If you see the same galaxy appearing in 3 different places, you know that those 3 images must correspond to 3 different light paths that all started from the same source and all ended at our telescope. And the only way to satisfy that constraint is if the mass distribution has a very specific shape and magnitude. So by measuring the positions, shapes, and brightnesses of all the multiple images and feeding that information into sophisticated modeling software, researchers can create detailed maps of where every solar mass of material, visible or invisible, must be located in the cluster, and those maps reveal the four-way merger in exquisite detail, showing the four main dark matter peaks, the filamentary structures connecting them, and the complex substructures within each peak. One of the most spectacular aspects of the lensing in MACS J0717 is the diversity of arc morphologies. Some background galaxies are stretched into long, thin arcs that curve gracefully around the cluster core. These are called giant arcs, and they can extend for 20 or 30 arc seconds across the sky, which is about 1/10 the diameter of the full moon, making them easily visible in Hubble images as beautiful blue or red streaks, depending on the wavelength of observation. Other galaxies are stretched into nearly complete rings, sometimes called Einstein rings, which occur when the background source, the lensing mass, and the observer are almost perfectly aligned so that light gets bent around all sides of the lens equally, creating a circular or elliptical ring of light. And while perfect Einstein rings are rare, MACS J0717 hosts several partial rings where the alignment isn't quite perfect, but is close enough to create striking arc segments that wrap partway around the cluster. The colors of the lensed arcs also tell a story. Many of them appear blue in Hubble images, indicating that they're galaxies undergoing vigorous star formation, pumping out massive hot blue stars at rates that can exceed hundreds of solar masses per year. And this makes sense, because we're seeing these galaxies as they were in the early universe. When star formation rates were generally much higher than today, the universe was younger, gas was more abundant, and galaxies were in the rapid growth phase of their evolution. So the fact that many of the lensed galaxies are blue and star-forming gives us a window into that era of cosmic history when the universe was building its stellar populations. But some of the arcs are red, indicating older stellar populations and less active star formation. And these red arcs are particularly interesting because they suggest that even in the early universe, there were already some galaxies that had formed most of their stars and were beginning to settle into a more quiescent state. And studying the balance between blue star-forming galaxies and red quiescent galaxies as a function of cosmic time is one of the major goals of extragalactic astronomy, and gravitational lenses like MACS J0717 are essential tools for that work because they let us see faint, distant galaxies that would otherwise be invisible. The magnification provided by the lens also allows spectroscopy of high redshift galaxies, normally taking a spectrum of a galaxy at redshift 6 or 7, meaning we're seeing it as it was when the universe was less than 1 billion years old, requires enormous amounts of telescope time, because the galaxy is so faint that you need to collect light for many hours to get enough photons to spread out into a spectrum. But if that galaxy is magnified by a factor of 20 by a gravitational lens, it becomes bright enough that spectroscopy becomes feasible with much shorter integration times. And spectra are incredibly valuable because they tell you not just how bright a galaxy is, but what it's made of, how fast its stars are forming, what its metallicity is, meaning what fraction of its gas has been enriched with heavy elements from previous generations of stars, and how fast the galaxy is moving, both its overall redshift, giving its distance and internal velocity dispersion, giving information about its mass. MACS J0717 has been used extensively for this kind of high redshift spectroscopy, taking advantage of the magnification to study galaxies that would be inaccessible otherwise. And some of the results have been surprising. For instance, researchers have found galaxies at redshifts around 6 that already show signs of chemical enrichment, with metallicities approaching 10 or 20% of solar values, which means that even when the universe was less than 1 billion years old, there had already been multiple generations of star formation, enough to convert a significant fraction of the primordial hydrogen and helium into heavier elements like carbon, nitrogen, oxygen, and iron. And this puts constraints on models of early galaxy evolution, suggesting that star formation must have started very early, perhaps just a few 100 million years after the Big Bang. The time delay between multiple images of the same galaxy is another fascinating aspect of gravitational lensing, because light taking different paths around the lens travels different distances and passes through regions with different gravitational potentials. It doesn't all arrive at the same time. If a background galaxy happens to have a supernova or some other time variable event, that event will appear in one lensed image first, and then in the other images hours, days, weeks, or even months later, depending on the geometry. And by measuring these time delays, astronomers can do something remarkable. They can determine the Hubble constant, the expansion rate of the universe, because the time delay depends on the distances to the lens and source, and on the expansion history connecting them. So if you can measure the delay precisely, and you have a good model of the lens mass distribution, you can work backward to figure out what the expansion rate must be. And this has become an important independent way to measure the Hubble constant, complementing other methods based on the cosmic microwave background or supernova observations. For MACS J0717 specifically, the time delays haven't been as thoroughly exploited as in some other lensing clusters, because it requires catching a transient event in one of the multiply image background galaxies and then monitoring to see when it appears in the other images. But the potential is there, and with the advent of wide-field time domain surveys that monitor large swaths of sky, looking for variable and transient phenomena, it's likely that future observations will catch such events and allow this kind of time delay cosmology to be done with MACS J0717's lensing system. The cluster's lensing power also extends to studying the cosmic web, because MACS J0717 sits at a node where multiple filaments of the large-scale structure converge, and those filaments, while much less dense than the cluster itself, still contain enough mass to produce weak lensing effects, the subtle coherent distortions of background galaxy shapes that reveal the presence of foreground mass, even when that mass isn't concentrated enough to produce the dramatic arcs of strong lensing. And by mapping the weak lensing signal around MACS J0717, astronomers have traced filaments extending for tens of megaparsecs from the cluster, showing how matter flows along these cosmic highways and feeds into the merger event. And this connection between cluster-scale physics and the large-scale structure of the universe is one of the most important areas of modern cosmology, because it tests our models of structure formation, how the universe evolved from the nearly uniform state we see in the cosmic microwave background to the highly clustered state we see today, with galaxies, clusters, and voids. The technical challenges of modeling the lensing in MACS J0717 are substantial, because this isn't a simple, relaxed cluster with a smooth mass distribution. It's a chaotic four-way merger with multiple mass peaks, substructures, filaments, and asymmetries. So creating a lens model that can accurately predict the positions and shapes of all the observed arcs and multiple images requires sophisticated software and significant computational resources. Researchers use techniques like parametric modeling, where they assume a certain functional form for the mass distribution, such as a sum of elliptical profiles for the different subclusters, plus additional components for the dark matter halos of individual galaxies. And then they fit the parameters of that model to match the observations, or they use non-parametric methods that make fewer assumptions about the form of the mass distribution, and instead solve directly for the surface mass density that best reproduces the lensing data. And both approaches have strengths and weaknesses. Parametric models are easier to interpret physically, but can miss features if the true mass distribution doesn't match the assumed form. while non-parametric models are more flexible but can be harder to interpret and may fit noise in the data if not carefully regularized. Despite these challenges, the lens models of MACS J0717 have reached impressive levels of sophistication, capable of reproducing the positions of multiply image systems to within a fraction of an arc-second, which at the cluster's distance corresponds to a few thousand light-years. And these models have revealed fascinating details about the cluster's structure. For instance, they show that the dark matter distribution is clumpier than you might expect if it were smoothly distributed. Instead, it shows multiple peaks and substructures corresponding to the individual galaxies and groups within the cluster. And the fact that these substructures can be detected through lensing, even though they contain only a tiny fraction of the cluster's total mass, is a testament to the power and sensitivity of gravitational lensing as a mass mapping technique. The future of lensing studies with MACS J0717 is bright. The James Webb Space Telescope, with its infrared sensitivity and high resolution, is now observing lensing clusters and pushing to even higher redshifts, finding galaxies that formed just 200 or 300 million years after the Big Bang, and studying them in unprecedented detail, thanks to the magnification provided by clusters like MACS J0717. And these observations are revealing a universe that was surprisingly mature at very early times, with galaxies that are more massive, more chemically enriched, and more structurally complex than many models predicted, challenging our understanding of how quickly structure could form in the early universe. MACS J0717's role as a cosmic magnifying glass will continue for billions of years into the future. As long as there are galaxies behind it, emitting light, and observers in front of it to collect that light, the cluster will continue to warp spacetime and create those beautiful arcs and multiple images, turning destruction into discovery and violence, into a tool for exploring the deepest reaches of cosmic history. And in this way, the cluster serves a dual purpose. It's both a subject of study in its own right, a laboratory for understanding cluster mergers, dark matter, and plasma physics, and an instrument for studying everything beyond it, the high redshift universe, the cosmic web, and the fundamental parameters that govern the expansion and evolution of space itself. The chaos unfolding in MACS J0717 isn't a frozen moment, but an ongoing transformation that will play out over billions of years. And when we look at this cosmic collision zone, today we're witnessing just one frame in an epic movie of structure formation that began long before our solar system existed and will continue long after our sun burns out, leaving behind something entirely different, a massive relaxed supercluster that will become one of the dominant gravitational anchors in its region of the universe. And understanding what comes next requires thinking about timescales that dwarf human history and dynamics that operate on scales larger than anything we experience in our corner of the cosmos. Right now, the four galaxy groups are still in the early to middle stages of their merger. They've made their first close passes. Their gas clouds have collided and shocked and heated to those incredible 100 million degree temperatures. The dark matter halos have interpenetrated and are now oscillating around each other in complex orbits, dictated by the combined gravitational potential. And the galaxies themselves are being flung about on trajectories that will carry them back and forth across the cluster core multiple times before they finally settle. And this settling process, called virialization, takes an enormous amount of time because the structures involved are so large that even at speeds of thousands of kilometers per second, it takes tens of millions of years for a galaxy to cross from one side of the system to the other. And the groups need to make several complete orbits, exchanging energy through gravitational interactions and dynamical friction before the system can reach anything like equilibrium. Computer simulations of cluster mergers suggest that a system as complex as MACS J0717, with four major components colliding from different directions, will take somewhere between 1 and 3 billion years to fully virialize, and during that time, the appearance of the cluster will change dramatically. The bright X-ray emission we see today, powered by shock heating and ongoing collisions, will gradually fade as the gas radiates away its energy and cools. The shock fronts that currently stretch for millions of light years will dissipate and merge into the background. The radio relics, marking those shocks, will fade as the accelerated electrons lose their energy and the magnetic fields decay, and the multiple distinct mass peaks visible in today's lensing maps will merge into a single, roughly spherical dark matter halo surrounding the new supercluster core. The final merged system will be one of the most massive structures in the local universe, with a total mass likely exceeding 2 or 3 times 10 to the 15th solar masses, equivalent to several thousand Milky Way galaxies, and a size stretching over 20 or 30 million light-years from edge to edge, making it what astronomers call a fossil group or proto-supercluster, the kind of massive gravitationally bound structure that represents the end point of hierarchical structure formation in the standard cosmological model. And once formed, this supercluster will be stable for many billions of years, held together by its own enormous gravity, while the rest of the universe expands around it. But even as MACS J0717 settles into this new configuration, it won't be truly isolated, because the cluster sits at a node of the cosmic web where multiple filaments converge, and those filaments, long streams of galaxies and dark matter stretching for tens or hundreds of megaparsecs through the intergalactic voids, will continue to funnel material into the cluster long after the initial four-way merger is complete. And observations have already detected at least one prominent filament extending southeast from MACS J0717, a stream of galaxies and gas that's at least 13 million light-years long and is actively feeding matter into the collision zone, adding to the chaos and ensuring that the cluster will continue to grow even after the main merger is finished. This ongoing accretion along filaments is a fundamental prediction of the cold dark matter model of cosmology. In this picture, the universe's matter isn't distributed uniformly, but is organized into a vast cosmic web, with most of the mass concentrated in filaments and nodes, while enormous voids contain relatively little material, and galaxy clusters form at the intersections of these filaments, at the nodes where matter flows converge. So a cluster like MACS J0717 isn't just a random collection of galaxies that happen to collide. It's a natural consequence of the large-scale structure. Matter has been flowing along these filaments for billions of years, building up at the intersections and creating the dense environments where clusters form and merge. The future evolution of MACS J0717 is also intimately connected to the expansion of the universe and the mysterious force called dark energy that's driving that expansion to accelerate. Right now, the cluster's gravity is strong enough to hold its member galaxies together against the cosmic expansion. The escape velocity at the cluster core is high enough that galaxies bound to the cluster will remain bound indefinitely. But beyond a certain radius, called the turnaround radius, the expansion dominates, and material that's currently falling toward the cluster will eventually be carried away by the accelerating expansion before it can complete its infall. And this means that there's a finite window of time during which clusters like MACS J0717 can continue to grow, and that window is closing. Current estimates suggest that dark energy started dominating the universe's energy budget about 6 billion years ago, around the time the light we're seeing from MACS J0717 was emitted, which means we're observing this cluster during the final era of major cluster formation. In another 5 or 10 billion years, the expansion will have carried away most of the matter in the surrounding filaments, and clusters will no longer be able to grow by accreting new material from the cosmic web. Instead, they'll be stuck with whatever mass they've already accumulated, slowly aging and evolving in isolation as the universe expands around them. This makes clusters like MACS J0717 particularly valuable scientifically because they're among the last examples of major hierarchical structure formation in action. We're seeing the universe build its largest gravitationally bound structures in real time, and by the time intelligent observers arise in galaxies 10 or 20 billion years from now, there won't be any ongoing cluster mergers to study. All the clusters will have settled into relaxed equilibrium configurations, and the violent phase of structure formation will be ancient history. So in a sense, we're living in a special epoch, cosmically speaking, late enough that complex structures like galaxies and clusters have had time to form, but early enough that the universe is still actively building its largest structures through mergers on even longer timescales, trillions of years into the future. Dark energy will continue to push everything apart, and the ultimate fate of MACS J0717 becomes stranger and more melancholic. The cluster itself will remain bound, its internal gravity strong enough to resist the expansion, but it will become increasingly isolated as other clusters and galaxies that are currently visible recede beyond the cosmic horizon, their light redshifted to undetectable wavelengths, and eventually unable to reach us at all, because the space between us and them is expanding faster than light can travel. And if there are still astronomers living in galaxies within the MACS J0717 supercluster trillions of years from now, they'll see a very different universe than we do. Their telescopes will show a small island of nearby galaxies, the remnants of the merged cluster, surrounded by an expanding void, devoid of any other structures. They won't be able to see the cosmic microwave background because it will have been redshifted to such low energies that it's undetectable. They won't see distant galaxies or quasars or any evidence that the universe extends beyond their local supercluster. And unless they have access to records from earlier epochs, they might not even know that the universe is much larger and richer than what they can observe. But long before that far future arrives, MACS J0717 will undergo other changes driven by internal evolution rather than cosmological expansion. The galaxies within the merged cluster will continue to interact gravitationally, occasionally passing close enough to each other that they merge, combining their stellar populations into larger elliptical galaxies. And over billions of years, this process will transform the cluster's galaxy population. The many small and medium-sized spiral galaxies that currently populate the system will be converted into a smaller number of massive elliptical galaxies, red and dead systems, with little ongoing star formation, because most of their gas has been stripped away or used up. And this transformation from a population dominated by blue star-forming spirals to one dominated by red quiescent ellipticals is a general feature of cluster evolution that astronomers have observed by comparing clusters at different cosmic epochs. The brightest cluster galaxy at the center of the merged system, probably formed by the merger of several large galaxies from the original four groups, will become a true monster, potentially reaching masses of several trillion solar masses and sizes of hundreds of thousands of light years, making it one of the most luminous single galaxies in the universe. And these brightest cluster galaxies, often called BCGs, are fascinating objects in their own right. They're thought to grow primarily through cannibalism, accreting smaller galaxies that wander too close to the cluster core and get shredded by tidal forces. And they often host supermassive black holes at their centers, with masses exceeding 10 billion solar masses. And these black holes can dramatically affect the cluster's evolution by heating the surrounding gas and preventing it from cooling and forming stars, a process called AGN feedback. That's crucial for understanding why the most massive galaxies stopped forming stars billions of years ago. The hot X-ray emitting gas that currently permeates MACS J0717 will also evolve in interesting ways. Right now, it's being heated by shocks and turbulence from the ongoing merger, But once the system visualizes those energy sources, will turn off, and the gas will begin to cool, radiating away its thermal energy in the form of X-rays, and slowly condensing toward the cluster center. And naively, you might expect this cooling to lead to massive star formation as the gas accumulates in the central galaxies. But observations of relaxed clusters show that this doesn't happen, or at least not at the rates you'd expect, and the reason seems to be the central supermassive black hole in the brightest cluster galaxy. As gas tries to cool and flow inward, it eventually reaches the black hole, which responds by launching powerful jets of relativistic particles that plow into the surrounding gas and heat it back up, creating a feedback loop that regulates the cooling and prevents runaway star formation. And the evidence for this process is visible in X-ray images of relaxed clusters, which often show cavities or bubbles in the hot gas where the AGN jets have pushed the gas aside. MACS J0717 will presumably undergo this same evolution. Once the merger is complete and the system has settled into equilibrium, the central black hole will grow through accretion and mergers until it reaches the masses typical of brightest cluster galaxies, several billion to tens of billions of solar masses, and it will begin to regulate the cooling of the cluster gas, creating the same kind of feedback loop seen in other massive clusters. And this regulation is crucial for the long-term stability of the cluster, because without it, the gas would cool too rapidly and form far more stars than we actually observe in cluster galaxies. From a broader cosmic perspective, MACS J0717 represents a critical test of our understanding of structure formation, dark matter, and cosmology. The fact that we can observe such a complex merger in such detail, mapping the distributions of dark matter, gas, and galaxies, and measuring their temperatures, densities, and velocities, provides an unprecedented opportunity to test whether our theoretical models actually work. Whether the simulations we run on supercomputers, which are based on our best understanding of gravity, dark matter, and gas physics, can reproduce what we see in nature. And so far, the agreement is remarkably good. Simulations of four-way cluster mergers produce structures that look very much like MACS J0717, with similar mass distributions, temperature profiles, shock structures, and even similar offsets between the dark matter and gas. And this agreement gives us confidence that we really do understand the basic physics governing the universe's evolution, even if many details remain to be worked out. Yet there are still puzzles and surprises. For instance, the exact mechanism by which magnetic fields are amplified in cluster mergers isn't fully understood. The simulations can capture the large-scale dynamics, but struggle with the small-scale turbulent processes that generate and sustain magnetic fields, and the efficiency of particle acceleration at shock fronts, which determines how bright the radio relics will be, is still somewhat uncertain, and may depend on plasma physics that's difficult to model accurately. And these uncertainties mean that systems like MACS J0717 continue to be valuable laboratories where we can test and refine our understanding of the physics operating under the most extreme conditions. Looking at MACS J0717 today, we're seeing a snapshot of violence and creation happening simultaneously. Four massive structures colliding at incredible speeds, gas being heated to temperatures that exceed the cores of stars, dark matter streaming through the chaos, unaffected by the destruction around it, shockwaves propagating across millions of light years, magnetic fields being amplified and twisted into complex patterns, and through it all, galaxies continuing to form stars and evolve, seemingly oblivious to the cosmic train wreck happening around them. And this juxtaposition of destruction and creation is fundamental to how the universe works. Structures grow by merging and destroying smaller structures. Order emerges from chaos, and the violence that tears apart individual galaxies builds the massive clusters that will dominate the universe's large-scale structure for billions of years to come. When you consider that this entire cosmic drama is playing out more than 5 billion light-years away, that the light we're seeing was emitted when Earth was still a molten ball of rock being bombarded by asteroids, and that the processes we're observing are shaping structures that will persist long after our sun has died and our galaxy has merged with Andromeda. It's humbling and awe-inspiring in equal measure. MACS J0717 connects us to the deepest rhythms of cosmic evolution, reminding us that we're part of a universe that's constantly changing, constantly building and destroying, and rebuilding on scales that dwarf human comprehension, and that the violence we see in this collision zone isn't random destruction, but a necessary part of how the universe creates its grandest structures, the seeds of future superclusters that will define the cosmic landscape for eons to come. And perhaps somewhere in one of those galaxies, being flung about by gravitational forces beyond imagining, other beings are looking out at the cosmos and wondering about their place in this vast, violent, beautiful universe, just as we are, separated from us by billions of light years and billions of years of time, but connected by the same fundamental forces and the same cosmic story of matter gathering, colliding, and transforming under the inexorable pull of gravity. And that connection across space and time is perhaps the most profound message that MACS J0717 has to offer. A reminder that we're all made of matter, forged in the hearts of stars, and scattered across the cosmos by events like this one, and that our existence, brief and fragile as it may be on cosmic timescales, is nonetheless part of the grand epic of the universe's evolution, from simplicity to complexity, from the smooth plasma of the Big Bang to the rich tapestry of galaxies, clusters, and conscious beings that populate the universe today. Chivuds